In machine learning applications, when we are developing a classification model, usually our initial models are not the best ones. So we have to make some extra effort to improve the classification performance of a model. So today we are going to take a look at how to improve classification performance and create a model that gives high classification performance. So today we'll go over how to improve classification performance. I'll start with one example explaining like why sometimes we have issues even when we develop a machine learning model. It may not be giving us results that we want, and we are always looking to do better. And then we'll go over something called ensemble methods, and especially bagging and boosting. So I'll give you very simple examples, and then we'll see how to do them in R. So that's the plan. So the example we'll use is our student applications example. So this is something we have looked at earlier too, where goal is to classify student applications as admit or reject. Student apply to a graduate school, and then based on their applications where there is information about GRE, GPA, rank, and then somebody makes a decision whether to admit or not. So this is a binary classification problem because our response has only two values. Our dependent variable or target has only two values. So whether the student was admitted or student was not admitted. So this is similar to what you have in the Kaggle competition. There also you have a response with two values. So one of the methods that we can apply is the decision tree. You can see this decision tree uses GPA as the most important variable at the top, and then classifies that into or splits into two parts. You have less than 3.4 and more than or equal to 3.4. If it is less than 3.4, so this model says reject. So reject that applicant. And then we also have a probability of 78%. So the data that was available in that we had this situation about 78% of the time. And out of all the data that was used for developing this model, so this branch alone has 52%. So that's the sample size that you see, 52%. And similarly, if you look at the first terminal node, if you reach there, if you get applicant, look at GPA, GRE, and rank, and if you end up here, that means your decision is expected to be accept. So 0.2 means there is a 20% chance of rejection. In other words, there is 80% chance of acceptance. So all the numbers are in terms of rejection. So when you see small number, that means these candidates are likely to be accepted. And then you have percentages. If you add all the percentages from terminal nodes, that will be equal to 100, which means 100% of the data. So obviously 9% in the first terminal node, so that's a good amount of data. And 52%, that means this college is rejecting more than 50% of the applicants. This was based on training data. So if we create a confusion matrix that you see at the top, the first confusion matrix, this is based on test data. I have not included training data because usually test data which is unseen by the model is more important. So we want to see how it performs on new applicants. So students actually accepted and also predicted to be accepted. We have 6 such people. So that's correct classification. Similarly, 72 actually rejected and model also says reject. So 72 correct predictions. So 72 and 6 are our correct predictions. And based on that, if you calculate accuracy, it comes to 67.8%. So this model is accurate 67.8% of the time. So not a great performance, but not that bad also. Roughly 68% accuracy is what we get with the new applicants. But we also notice that this model is doing a better job of correctly predicting candidates that will be rejected, 72, compared to acceptance. Majority of the people are here rejected actually. So there is a misclassification at a very high level when it comes to correctly accepting applicants. 6 times 4 is 24. So 4 times more misclassification for accept category. Usually when we have data which are slightly imbalanced, not like exactly 50-50, we don't have a situation where 50% of the students are accepted and 50% are rejected. Even if you look at this decision tree here, in terminal nodes, if you just do a rough calculation, the reject boxes or terminal nodes, you have 7%, 6%, 9, 5 and 52. Roughly 79. So 79% of the data points belong to that category. So usually in those situations, we try to not only depend on accuracy, but we want to look at something more. Now the second confusion matrix that you see, except row for predicted is 0, 0. So this is not based on this tree. What we are saying is, let's reject every applicant. So that's our prediction model. So everybody is rejected, nobody accepted. So if you calculate accuracy for this, so obviously 85 is correct prediction, because in the actual data 85 were rejected and the model also says 85 should be rejected. So 85 divided by the total. So total here is 30 plus 85, 115. And that percentage of accuracy comes to 73.9%. So even better than the decision tree model. The accuracy that you got for decision tree was only 67.8%. So now you have a better accuracy, but you can see this model is worthless because you are simply saying reject everything. For the first model, which was inferior, if you calculate AUC, if you do a ROC curve and calculate area under the curve. So if you recall, in ROC curve, your curve should be higher than the diagonal. If it is exactly on the diagonal, that means your model is not doing better than toss of a coin. So without a model, we can get better results than this model because AUC is 0.45. And you can see in the second matrix, AUC, if you calculate, it will be 0.5, 50%. A very rough calculation, you are correctly predicting reject 100% of the time and you are correctly predicting accept 0% of the time. So you have 100% and 0%. So if you take average, that will be roughly 0.5. Now if you do the other way, let's say your model is accept everybody. Whoever applies, so your model says let's accept it. So 30 here and 85 here, and reject row is 0, 0. So now if you calculate accuracy, so obviously you are correct 30 times. So 30 divided by 115, if you calculate, that will give you 26.1%. So these two very bad models where we are not using any machine learning, they are giving you a range from 26.1% to 73.9%. So sometimes it's very difficult to rely on accuracy, especially in these kind of conditions where your data is not balanced. So a better way to look at it is area under the curve. So area under the curve here gives you much better information. But then we can actually create another tree model and hope that it performs slightly better. Instead of 67, we may get slightly higher accuracy or slightly better AUC. But one problem with a single tree model, although it's very user friendly, you can see like what's going on, you can visually see and relate to this, and anybody can implement it very easily, because once you develop the model and give it to a person, they can very easily understand what's going on and make a decision. But the only drawback of a single tree is that usually they are not very accurate, and you have seen that in many of our homework assignments, where you find some other methods to perform better than a tree model. But tree is very useful for classification type of problems. So let's see how we can improve this classification performance and get better AUC, or area under the curve. That basically brings us to ensemble methods, where you combine various methods and then make a decision. Instead of depending on one, you may feel that there will be better result if you can combine more than one methods. So this picture actually shows you a story where an old man had four sons, and he was on a deathbed, and he knew that his sons are always fighting. So he wanted to teach them a lesson so that after him they can live happily. He asked them to bring some sticks and asked them to break those sticks. So each one of them, all those boys were like very strong, so they were able to easily break those sticks. And then he asked to combine four sticks together and asked each one of them to try and break, and they were not able to break. So I'm sure you have heard this story. So obviously there is a strength in numbers. If we get like results from more than one tree, so that is likely to give us better outcome. So this is an example of a weather forecast. So you have reality at the top. So some days you have thunderstorms and some days you have sunny. So that's the reality after the fact. But then before these things happen, maybe there are different models. The first model predicts that on day one it is going to be a thunderstorm, cloudy, and also predict the same thing for the second day. Out of 1 week, three times first model is wrong. It happens actually in Dartmouth also, like sometimes there's a prediction of a storm and nothing happens. Or sometimes there's a prediction of a snowfall, nothing happens. Sometimes there is no forecast about snowfall and suddenly we see snowfall. Then there is a second method which makes these predictions, which is again incorrect three times. If you take votes, you can see that on day one, 4 out of 5 are predicting thunderstorm. So if somebody combined those results into one, they could have done a very accurate forecast. Same thing for second one. So 3 out of 5 predict that there will be a sunny day, and that's a correct prediction. So you can see your predictions become much more accurate even when individual predictions are not that accurate. So that's the whole idea behind combining results of various models. So one of the methods is called bagging. This bagging comes from Bootstrap aggregating. So it borrows a B from Bootstrap and AGG and last ING. So that becomes bagging. So what is a Bootstrap? It's a random sampling with replacement. So Bootstrap basically is you take repeated random samples with replacement. So you take a sample and replace it, again take a random sample and replace it, and what happens with that is that everybody has equal chance of getting selected, and that can also lead to some data points getting selected more than once. Let's say you have entire data that you break into two, training data set and test data set. So this we do only with the training data. So you take random sample with replacement from the training data and create one subsample, you can say. You repeat that process and you get the second subsample, call it data 2. Repeat it, you get data 3, and similarly you can get as many as you like. So k is a number that you choose. It could be 10, it could be 20, it could be 100. And then you create your model. So typically it could be a tree model. So using data 1 you create model 1, using data 2 you create model 2, 3 gives you model 3, and data k gives you model k. So now you have so many different models. And then what we do is what we did in the previous slide, we take majority vote. So this we do for each and every case. So first applicant, second applicant, third applicant, we try to find what is the majority vote, and that becomes your final prediction. We don't depend on one decision tree, but we create multiple decision trees. And it's very easy to do using R, because you can create as many trees as you like. 100, 500, 1000. So it's very easy. Okay, let me show a quick example in R. I ran this code for bagging, where admit is the response variable, and I used train data. And using a Bootstrap process, we created 10 samples, and we created very shallow trees. So maximum depth here is just 1 tree based on the first sample. So for that, this is the tree. It uses GPA as one of the variables. Similarly, you have the second tree, third, and so on. And this is the 10th one. Now looking at the votes, first applicant has actually 5, 5, so there is a tie. And second applicant has 10 votes for first category and 0 votes for the second category. So very clear-cut winner here. Third one has 1 versus 9. So this way we have this for all the applicants in the training data, a total of 285. And then probability or proportions are based on the voting data. So we had 5, 5. So 5 out of 10 is 0.5 and 5 out of 10 is 0.5 here. In this case we had 10, so that becomes 1 and other becomes 0. So we have these probabilities for all 285 applicants. Based on that, the first applicant is rejected, second applicant is accepted, and so on. It also gives us what samples went into data 1, data 2, data 3 up to data 10. And you may also notice that, for example, in data 9, we can see that 6 appears more than once. So because sampling is with replacement, we do see repetitions very often. So this output shows us how bagging works. So this process is called bagging. Another method or another approach for developing an ensemble method is called boosting. So once again, in boosting we start with training data. From the training data we take Bootstrap random sampling with replacement. Data 1 is a random sample with replacement from training data. And then we create model 1, which could be a tree. But then from model 1 you see an arrow going back when data 2 is being decided. I'm talking about this arrow. When you have this model and when you have the results of this model, you know that how often mistakes were committed, how many times we had mismatch. Actually, a student was admitted, but the model says it should be rejected, or the other way. When data 2 is collected from training, what is done is we give more weightage to those applicants where errors occurred, like misclassifications occurred. I have noted at the top, data 2 basically learns from mistakes of model 1. Misclassified examples appear more often and correctly classified examples appear less often. So if there were like 100 applicants, those cases which were correctly classified, so when taking data 2 randomly, we select less of those cases, but we select more of those cases where mistakes were made. So basically, When we develop model 2, it has learned from the mistakes of model 1, so it is likely to be better in classifying at least those cases where mistakes happen. Now model 2 output in terms of its performance, like which cases were correctly classified and which cases were incorrectly classified, that becomes input to data 3. So when random sampling with replacement from training data is done for data 3, we again give more weightage to misclassifications and less weightage to correct classifications. In a way, you see this model 1, model 2, model 3 up to model K, they go in sequence. When this process runs, it is not done in parallel. Data 1 to data K, they are not used for creating model 1 to model K in parallel. So in bagging, it happens in parallel because each data is independent of the other and each model can be made independent of the other. But in this case, it goes in a sequence. So obviously, it will take more time to run this algorithm. But ultimately, what happens when you have to come out with the final decision, we make use of linear combination of weighted votes. These weighted vote means those models which perform better have a higher weightage, and those models which are like inferior, they have less weightage in the final classification of each applicant. So final classification is basically more complicated here. It's not a simple majority vote, but it is a weighted average based on weights of each model. That's what is called boosting, but apparently boosting algorithms really help to improve performance of a classification model. And in fact, when it comes to solving classification problems and winning competitions on Kaggle, we have found that one of the algorithms called extreme gradient boosting, that is very, very popular. So a lot of people use that algorithm to get better outcome. So there are like various forms of boosting algorithms. The how these weights are taken and what is the approach for implementing it may vary from one type of boosting method to other type. And same thing is true for bagging also. So there also there could be different approaches for implementing what we discussed.
Professor, on the bagging one, right? When you says that it's taking a bootstrap to get data, is it just using the data that exists, or is it making synthetic data?
So when you are doing bootstrap random sampling with replacement, you are using the existing data. Let's say my training data has 285 applicants with GRE, GPA, and rank of the college from where they are coming. So out of those 285 applicants, this data one will be randomly selected with replacement. So it may select applicant number 10 first, then applicant number 100, applicant number 193. Again, it may select 193 because it is with replacement and it's done randomly. So it doesn't make up anything. It is selecting from the same data, but it is selecting with replacement. Let's go to the next slide. So I showed you earlier, like when we make a single tree, what happens, what accuracy we get, and what area under the curve we get. So this is the result of bagging, and this is a more detailed confusion matrix that we'll create today. So this is based on test data, and we have 67 correct applicants who were rejected and 9 correct applicants who were accepted. So that gives you accuracy of about 66%. And there are a lot of values here, but another thing that is important and that you are aware of is sensitivity and specificity. We don't want a situation where there is a huge difference, like one is 0% and other is 100%. So that's also not good. So sensitivity here is 30% and specificity is 79% roughly. So what is sensitivity? You can see a student getting accepted 9 times, and the model also says that this should be accepted. So 9 divided by 9 plus 21, which is 30. So that is 30%.
Yes.
And similarly, 67 divided by this total is 78.8%. So those are the numbers which are important. But when you look at ROC curve for the test data, you find that AUC, area under the curve, is now more than 0.5. So this diagonal is for 0.5. So by bagging, we are able to get outcome which is more meaningful than what we had earlier. So the red line is for tree, single tree, and the green curve is for bagged trees. This is with boosting. We have 63 and 12. So specificity has gone slightly down from 78% to 74%, but sensitivity has gone up by 10%, like 30 to 40 now. And you can see area under the curve based on the blue line, which is for boosted trees, is about 63%. So while creating these models, whether it is based on bagging or boosting, so many times we may have to play with the model a bit because they have some hyperparameters that we need to change and see what happens. Very often, a lot of experimentation is required to get better results. So we'll go into R now and make use of this data and carry out this analysis that I showed you, which can help us to improve our classification performance. So you can open your Kaggle page and go to notebooks and then say plus new notebook. So we'll create a new notebook. We are using R and the type we are going to use is notebook. We will leave these as defaults and click on create. We can get rid of this. So I'll simply name this as Ensemble. So we are going to need some libraries. First one is called ADA bag. So ADA for adaptive and BAG for bagging. Another one we'll do is R part, which is the recursive partitioning dot plot. So this will help us in plotting our tree. We'll also use P and capital ROC. So this will be for our rock curve. And another one I would suggest is XG boost. So extreme gradient boosting. So that's the most popular boosting algorithm for classification problems. I'm also going to put DPLYR just in case. So I'm not sure whether we'll need it, but just in case. So you can run these. If I run this again and don't see any error, that means everything is fine. So for data, let's click on this plus add data. And then your data. We have used this earlier. You'll see there is a binary.csv file. We can select that. It says binary is ready to use. If you expand this, you can see binary file is there. Okay, let me do this. We can also say header equals capital T. So this is our data that you are familiar with. So everyone able to use this data or read this file?
Yes, Professor.
Okay, so we'll keep moving then. So after that, I'm going to data preparation, because we need to change admit and rank to a factor. I will do another thing, data $. This is only for the response variable. So you can see response variable is currently 0 or 1. 0 means rejected, 1 means accepted. So sometimes there could be confusion, like unless we label it somewhere. So what I will do is I will use if else, and we can say data $admit equal when it is 1, let's name it accept. So student is accepted, else reject. So wherever you see 0, it will change to reject, and wherever you see 1, it will change to accept. And typically when we do this in R, we have seen that it treats that variable as a character. So we still need to do admit as dot factor. We need to convert this into a factor. We do the same thing for rank. We can also again do str data just to confirm whatever we did, it reflects the way we want our data to be. So run. So you can see admit is a factor now with accept and reject values. Rank also is factor. For reproducibility, so that you have same training and test data as me, we will use set dot seed. So let's use 1 2 3. So we are taking independent samples of size 2, where number of rows we want is whatever we have in data. And for replace, which is whether it is with replacement or without replacement, we are saying we want with replacement. So replace equals true. And then probability for those two subsamples. First one we can say 70% and second one 30%. Basically I'm doing what we have done many times. Data where I and D is 1 becomes train. So after 1 there is a comma, and the other one becomes where I and D is 2 comma becomes test data. So let's run this. So obviously there is no output here, it just creates training and test data. We can add new code. So the first thing we'll do is we'll create a single tree, and because these trees are created at random, so let's fix the randomness using 1 2 3 4. We'll save our tree model in tree. and we are going to do recursive partitioning. So R part admit variable is the response variable as a function of GRE plus GPA plus rank, and our data is in train. So this is how we develop our tree model. You can also do R part dot plot to plot our tree. Run this and it creates this tree. Let me do something more here. We can set type equals 5. So this is more compact. So everyone with me so far?
Yes.
Okay. This algorithm that we use here, R part or recursive partitioning. So typically, like whatever algorithm you use, they may have some hyperparameters or the parameters that needs to be explored or changed. For example, for R part, if you just want to see what this model has as a hyperparameter, so lookup, model lookup, L is uppercase, and then we can say within quotes R part. You can see that it has only one parameter. It's called CP. So the full name is a complexity parameter. It can be used for even regression problems as well as classification problems. So for class means for classification, and trees can be used for both regression. Regression means your y variable is numeric, so it can be used for both classification and regression problems. And you can also get probability as output. This model lookup can give you information about like how many parameters your model has. Let's look at model performance now. So for confusion matrix, we'll do it only for test data. So it can be done very easily for both. We need to make prediction using predict, and our model is called tree, and the new data unseen by the model is in test, and the type of prediction that we want is class. So we are not looking for probability but just a class. For confusion matrix, we can say confusion and then M uppercase matrix. So we want it between P and test data $ admit. So this is a kind of confusion matrix that I showed you. So it gives you the table as well as calculation of accuracy. It also calculates sensitivity and specificity. So this is the exact same confusion matrix that I showed you in the PowerPoint. So this is one thing that we do. And in the PowerPoint, I use this model for finding the rock curve. So let's do the rock curve using predict. The model is tree and new data is test, but this time instead of final class, because in ROC we need probabilities, so just classification will not do. To get an entire picture we need probabilities, so we have to say PROB. This will calculate probabilities and store that in P. So let me run this, and then if you select P and run, you see you get probabilities. So these are the cases in test data: second applicant, fourth, fifth, eighth, and these are the probabilities of acceptance and rejection. But note that there are two columns, accept and reject. When we make the ROC curve, we need just one of them. We don't need both. What I'm going to do is I will store these calculations in ROC, and the function for ROC is ROC, and it needs the response in the test data and these predictions. But the problem is in P we have two predictions, but we want only one. We want to select only one of the columns, and if you want to specify a specific row or a column, you can use square brackets and then say comma. Before comma we don't put anything, which means we want all the rows and we want first column. So it will give us what is the probability of student getting accepted. That's what we'll store in ROC. Let's also, like before we plot, let's use a function called AUC, area under the curve, and ROC. So that will calculate what is the area under the curve, and then we can also plot ROC. So in this part we are predicting probabilities, storing that in P, and then calculating area under the curve AUC and plotting the ROC curve. So it gives us this AUC, area under the curve, as 0.45. That's what I had in our PowerPoint, and this is how your plot looks like. This goes below the line. If you want a different color, like default is black, but if you want a different color, you can always go back in your plot and say color equals, so let's say 2, C2. So it gives you red color ROC curve. So everyone is getting the curve?
Yes.
Okay. Let me do one more thing. We'll create this tree again, but we'll do that in a different way. So we'll do a tree with cross validation. What is cross validation? We can split the training data into different parts, maybe 5 parts or 10 parts. And if we have like 5 parts, first it will create a model with first 4 parts and the last part is not used. So that is used for assessing error. And then it will create again model with other 4 parts and leave the 5th one out and calculate error based on that. So it will repeat this 5 times. What I will do is I will again do set.seed for repeatability 1, 2, 3, and we will store the cross validation related information. So let's store that in CV, and the function that we use is called train control, where C is capital or uppercase. So train control, we will define a method, and what we'll do is we'll not only use cross validation, but we'll use a repeated CV cross validation. So we'll repeat it few times. So that's one thing we'll control while training. Another thing we can control is the number. So how many cross validations you want. If you want to split our training data itself into different parts, let's do 10. And then you can repeat the whole thing few times. So we'll say repeats equal So let's repeat everything 5 times. I'm also going to allow parallel calculations. So we'll say allow parallel equals true. So we can say our new tree model, and we are going to train it like this. So the function we use is called train. Admit is our response variable as a function of dot, so all other variables. So let's hit enter and say our data equals train. Then it will ask you what is your method, what method do you want to use. So let's say we want recursive partitioning, so R part, and then TR control. So we can say we want CV that we defined in the previous line. And one more thing, tune length. So this R part algorithm has hyperparameter called CP. I think we defined it here. This one, complexity parameter CP. So how many CPs we want? So that's what this tune length can tell us. When it is searching for the best outcome, we'll say we want it to report 10 CPs. If you want to write down a note for that, you can say number of CP values. So that's what you get here. And after that, if you simply want the output of the tree, you can say tree. So let's run this. So it gives you some information that training data has 285 samples. And we did cross validation. We used 10, this number here 10. So it was a 10-fold cross validation, which was repeated 5 times because repeats is 5. So when it split training data into 10, so first subset was 256, second one was 256, 256, 257. So we have those 10 different sample sizes, and we also asked it to report 10 CP values. You can see you have 10 CP values. In this example, the model finds CP of 0.0229 as the best outcome. So this one, you can see it gives highest accuracy. I'm going to copy the CM part and paste it here. I'll also copy ROC part and paste it here. So when you run this, in the previous part, basically we are making use of a package called, a very popular package for machine learning called Carrot. And when we are using that, actually instead of class, it calls it raw. So we'll use the same term that Carrot needs. And everything else remains same. So it gives you confusion matrix, accuracy, sensitivity is very low, specificity is very high. You can see 71 and 5. Now in terms of ROC, ROC is 55%, which is a better result than what we got without cross validation. Okay, so now we are moving to the first ensemble method called bagging. And let's copy the tree part and paste it here. I will also add extra line for set.seed. 1, 2, 3, 4. We need to make some small changes here. So method, instead of R part, we'll use tree bag. That's the method we use for bagging. We'll leave our cross validation as it is. And because that CP was the concept of the tree, it doesn't apply to the bag. So we don't need this tune length. But I'm going to add importance feature. So that will give us like which variable is important and how much. So we can say this is true. And we can also say plot VAR and then uppercase I MP for variable importance. And let's differentiate between the models. So instead of tree, we'll say this is a bag model for bagging. So we'll use bag here. And then you can run this. Okay, so we get the output. So it says after all these cross validation and repeats that GPA is the highest contributor to the model accuracy, followed by GRE. And rank do not contribute that much in this model. And I'm going to copy this whole part, confusion matrix and rock, because we can reuse that for the bag also. So if you run this, you get the confusion matrix. So we have 71 and 5.
I think you have to change the name from tree to bag, right?
Oh yeah, because that's what I thought. This looks like the previous one. So I have to change this to bag. Okay, so I think this should work. Okay, so we do see some improvement, 9 and 67 this time. And what I had earlier was 5 and 71. So from 5 it has gone to 9. So that's a big jump in correctly predicting accept. But it comes at a cost of little bit cost of reject. It gives us an accuracy of about 66%. Sensitivity is 30% now compared to much smaller earlier. Specificity has come down, but not that much. And if you look at area under the curve, obviously there is an improvement. So now it is 58%. And we can see that visually also. Let me do one thing. I'll go back at the top and let me locate the first rock curve that we had. Okay, so the first one, we'll call that as a rock. So we'll retain that name. And then for bagging, we'll call it rock 1. So we want to change the name to rock 1, and we'll also change the color. So later on, we'll combine the individual tree, bagging, and boosting in the same plot. So that's the idea. Okay, so we did bagging. So now let's develop a model with boosting. So I'll use the most popular one, and the one works better. It's called extreme gradient boosting. If you want to do model lookup, so within quotes we can say XGB and then uppercase T for tree. Actually, in lookup, L should be uppercase. So you will notice that unlike the first model R part where there was only one hyperparameter CP, extreme gradient boosting has 7 hyperparameters. So it provides us a lot of options, a lot of flexibility to fine tune and come up with the best outcome. But again, so it is going to be very tricky also, like how do you find the best value for number of rounds or number of iterations or maximum depth or eta, gamma, so all these. And just like a tree, this can be used for both regression and classification problems, and you do get probability values. So those are the good things. Let me copy this part and then we can modify this here. Instead of bag, we'll call it BOO for boosting. And the method is now extreme gradient boosting tree. We'll continue to use cross validation. I'm going to remove the importance part here. And I want to use something called tune grid. This is for tuning the hyperparameters that you see below. So we can specify what we want. This equals expand dot grid, and then we can go one by one, pick up the first one like number of rounds. So let me say we want 500 iterations, or let's go lower so that 200, so that it runs faster. And then the next one, max depth equals, so that's the depth of the tree. So maximum tree depth. So we don't want the trees to be very deep in boosting as well as in bagging. But this is a hyperparameter that you can play with and see. We don't know from the beginning what will work better. So I'm going to say 2. The next one is eta. 0.3. Okay, so eta is 0.3. Next one is gamma. So let me start with the lower gamma. And then we have subsample ratio of columns. So columns in our data are the variables. It has to make a decision like out of all the variables, how many it needs to use as a subsample. We can specify that. Let's say we start with 1. Minimum sum of instance weight, so minimum child weight. I'm going to say 1. Subsample. So subsample percentage. So what percentage you want to use while training the model. So if you want everything, say 100% 1. So let's run this. Okay, so it is very quick, it's finished running. So I'm going to copy again this part, confusion matrix and rock, and instead of bag we'll say boo for boost, and instead of rock 1 let's store it in rock 2. And then we'll use a new color 4, and I think we can leave everything as it is. So immediately you get confusion matrix where you have 11 correct predictions. So this is better than the previous one. I think last time it was 9 and this is 64. We can check. So this was 9, this has gone up to 11. It was 67, it has come down to 64. You can see area under the curve is better actually with this outcome. So that improvement for accepted candidates is boosting the area under the curve or the rock curve. So far you can see the gap is much bigger, and that's why area under the curve is more here. Let's plot all the rock curves. We can say comparison of rock curves. We plot the first one rock, and we use color as 2. Actually we can also give a title. This is 1, and then we want to add other plots. So this is how we can do. We want rock 1 where we used color 3. We also need to say before color add equals true. So this means we are adding this curve to the previous one, and we repeat this, copy this, paste, and instead of rock 1 you do 2 and color 4. We want like 3 different colors, color number 2, 3 and 4. We are not using 1 is black and 2 was red, 3 was green, 4 was blue. So we want these 3, and we can also add legend so that we know which color is for which plot. Okay, so where do we want this? We want it x equals bottom right, and legend we have more than one, so I'll use C. So first one is tree, second one is bagged trees, and third one is boosted trees. It's a title, so this is how it is going to look like. And then we can also say along with the legend we have to say which color, so that we can specify using fill. And we know that we use 2 for the tree, 3 for the back tree, and 4 for boosted tree. So if there is no typo, it should give us a plot. Okay, there is a typo. So OM, bottom right. So this is what it gives us. But what happened to the legend? So actually I don't see the first plot, rock. Let me run it again. So I'll run this and then the rock part. Okay, so now all the three plots appear.
Yes, Professor, but legend is not coming still now.
Yeah, I don't see the legend yet. Let me also add size of the legend. Okay, it's there, but it's, let me see if I can make it appear somewhere. Yeah, it's too big. Yeah, I think it behaves slightly differently on the website versus in RStudio. So in RStudio, when I say bottom right, it usually goes here. But it gives the idea. You can see the blue one is for boosted tree. So clearly it has more area below the curve compared to bagged, and red one is the first one that we created where it was less than 0.45. Anyone has any questions?
So does that mean that when Kaggle gives us a score, that score is always the area under the curve and not the accuracy?
When we have data which is not balanced, if it is a balanced data, then accuracy is very good because it gives you a good picture of what's going on. But if your data is not balanced, you have seen that if everything is 1, still you can get more than 70% accuracy, which is obviously misleading. And that's why in those situations, we make use of area under the curve because that's more appropriate compared to just looking at accuracy. In this curve, ideally, we should be in this corner. Specificity should be 1 and sensitivity should be 1. So that's the best or ideal situation to have. So these curves, if we are improving, like if you are making any changes to your even extreme gradient boosting model, let's say instead of 200, if we do 500, instead of max depth 2, let's try 5. Rerun this model and wait for it to complete its run. And find the ROC. And now if you plot, usually it's difficult to see whether the previous blue one was better or this one. So we have to look at a number, area under the curve. And area under the curve is 0.62. So it is slightly better. Earlier I think it was 0.61. And typically in Kaggle competitions, like moving by 0.1 or 0.2 can make you jump many steps on the leadership board. Especially like if your performance is already high, then improving by 0.1 is not easy. It's really tricky. So I think one of the questions in chat room, like why eta is 0.3. The value that I have put is actually a default value. In XGBoost extreme gradient boosting algorithm, default value is 0.3. So that's what I put. But these values can range from 0 to 1. It's basically learning rate, the rate at which our model learns patterns in the data. That's what is eta. If you make it too big, like if you want it to learn the patterns too quickly, it may complete iterations quickly, but there is a chance that it may miss some finer things. And if you put your eta too low, very close to 0, what it's going to do is it is going to learn too slowly And if your number of iterations are not good enough, because it is going to stop. If you are saying 500 rounds, and if we give eta very low and number of rounds are completed, then it may not have learned everything. But it's a good idea to actually explore below zero point 0.3 and above zero point 0.3, because 0.3 may be default. It may not work for every data and every situation. So I'm going to decrease this because I feel I have sufficient number of iterations. Let's see what it does. Our area under the curve right now is 0.62. So let's see if it improves or not.
So, Professor, we can change these parameters. We can check the outcome, right?
Yeah. So
Like an
yeah. So right now I ran with the changed parameters, and then so that's what is experimentation, right? Beforehand we don't know, but after you have been working with some type of data, when you are doing the trial and error, you may find some pattern emerging, and you may know that already, like after some runs, that higher eta is like useless or very useful, we don't know. And you may start getting some ideas by trying few values. So right now I see 14 accepted and 59 rejected. So those are the correct predictions. So slightly lower than our previous value. So 0.62, so this goes down. That means by reducing from 0.3 to 0.1 is not helping. So let me try 0.2. So this one also has the same almost. So it's not helping much by going below 0.3. That's what we see. How about going on the higher side compared to the default? I know some of you are from industrial engineering background, and you may have studied design of experiments. So this could be a good candidate for doing a design of experiment where you experiment with these features in certain range and carry out ANOVA and see what gives you the optimal outcome. Okay, so this one changes it to 13 and 59. Not a very huge difference. And the other thing is, gamma here actually can control overfitting. So gamma is a parameter that helps us to avoid too much of overfitting, because with trees, if you grow your trees too big, so right now I'm using actually 5 as a depth. So that is relatively bigger, especially when I'm doing boosting. So let's go to 3. Okay, so we run this 14 and 60. It may be better than the previous one, but yeah, so this is about 62.5% roughly. You see, by making the tree shallow, we got a better result compared to when it was 5. We don't want to go too down, like let's try 2. Okay, so this looks like we got better than the previous one also, 12 and 62. Or I think previous one was 14. Okay, so improvement here, but this one reduced.
So on an average, yeah, it's better.
But AUC is better. So there are some ups and downs, but overall it is giving you. So your score on Kaggle obviously will go up with this one. So far this is the best. This way you can do the experimentation, but I want to quickly also go over one more thing.
Professor, how about N rounds? Can we increase the N rounds? It will affect.
Yeah, so usually like 500 is good enough, but since it is a computer and it is running fast, let's try 1000. We run this 11 and 63,
Yeah.
but your overall AUC improves to 64%. If you are only looking at AUC, as a metric, then this is giving you even a better outcome. Okay, so now let me do one more thing here. We have 2 times more cases for candidates rejected compared to candidate accepted. So obviously the data is giving more weightage to those cases that are rejected, and the model tends to do better in those situations. Let's address this balance or imbalance, I would say. I will make a small table to see what is the level of imbalance. 97 cases where students were accepted in training data and 188 were rejected. So there is a clear class imbalance. So let's store in ACC. So we'll use our train data and connect this using percentage greater than percentage to do a filtering where we can say admit is accept. So ACC will contain only those applicants who were accepted, and after that we do REJ. There we have only those applicants who were rejected. So there will be 188 applicants in REJ and 97 applicants in ACC. So that's what these two lines will do. And then what I'm going to do is capital REJ for reject. So in reject we'll store out of 188 cases, we will store 1 to 97 just to have a number that matches with accept. All those rows and then comma, and after that nothing means all the columns. And let's create T where we do row bind ACC and REJ. So that ACC and REJ that we have created, so T will contain only those cases, 97 cases of accepted, 97 cases of rejected, so that we have a balanced data in our training data. So whatever we are doing here, we do it only for the training. We don't do it for testing because test results are not known, and typically not known because it is applied, like new applicants come in and then the model is applied there. So we don't want to touch test data. If you run this, and then what I will do is I'm going to copy this part so that we don't have to type it again. And the only difference is instead of train, I'm going to say T. And we'll also have confusion matrix and ROC done. So let's run this and see what we get. So it has completed the run and we have 16. So and this is 51. Okay, so right now AUC comes at 0.58. Although it is less than what we got there, 0.64, but we should not rule this out yet because we are running this with hyperparameters that worked for slightly different data. We may have to actually fine tune this to extract a better outcome. So it may call for some experimentation. So I see some improvement. This is now 18. In fact, both specificity and sensitivity are more than 50%. But let's see what happens to, so this is about 58.9. So this requires some more work, but this is another way we can try and explore by handling this through class imbalance. Okay, so I think I gave you some ideas of working with this. Let me save this for future use. Okay, so it's completing that, but any question, anyone?
Professor, I have a question. So when we're doing the rock curve, right, we use the predict with the type equals prob, right? But we can't use that to make the test data. We need to use type equal raw, right?
When we are using this train function for training the model, so that time when we are doing confusion matrix, while predicting, we are using raw.
All right, so that's what we use to make the file. All right.
Yeah. See, the first time I used a class, but that time I was not using the train function, but I was using directly R part. The train function, which comes from like correct package, that's much more versatile, because you can see with that train we were able to run bagging, boosting, and even the tree. Okay, any other question? Okay, so this is the situation as of now. This was a very quick overview of how to improve classification models, and we went through some ideas of bagging and boosting, and especially extreme gradient boosting is a very handy tool, although it requires a lot of experimentation, but it can get you very good results also. So thanks for your participation.
Bye, Professor. Good night.
Thank you.